This is your second lecture in the summer assignment, topic 1. So this is topic 1, part 2, and it has to do with measurement and problem solving. By now, you should have already discovered that you should be completing your own learning targets first using your textbook, and then watching the video to add to what you've put in your learning targets. So if you haven't yet made your learning targets, stop the video here, make your learning targets, and then come back to watch the video in a few minutes. So go ahead and stop it, and you can restart. So if you have your notes already, you're ready to go on and add to them as you watch the lecture. You probably have noticed that the lecture that I gave on part 1 really only partly goes with what you had already created, and that there are lots of things that you already created in your learning targets that I did not include in the lecture, and this is going to be the same. The things that I think are basic that you shouldn't need my help with and that are really review, I'm not including in the lecture. So please make sure you do a really good job of the learning targets, and now we're going to go add to what you know. You should be already really good at dimensional analysis and multiplying by fractions to convert from a different unit, from one unit to a different unit. Remember that conversion factors are equalities, but they are written as fraction form, and so the numerator and the denominator of the fraction have to be equivalent. And you can multiply by as many of these fractions as you need to change the units, as long as the numerator and the denominator represent the same thing. This fraction equals 1. So don't forget, this is going to be a really big thing as you go into AP Chemistry. We do a lot of dimensional analysis. So I'm going to encourage you, as you're working on the practice problems and as we look through this lecture, at this level, that you start to think about some conversion factors that maybe you wouldn't have thought of as conversion factors before. So we'll see how this goes. I do want to talk about problem solving, especially at the AP level. In your first year chemistry class, the problem solving is pretty straightforward. Typically, a question might be only one part. It's pretty clear what's given and what you're solving for. But at the AP level, they tend to lump together more than one step in a question, or maybe only give you a big question that you have to do multiple thought processes to solve. And so I do want you to think that you will need to be thinking about how to solve problems. And the first thing that you want to do, if you're not sure what you're doing, is start by figuring out what you'll have to do last. So figure out what the very last step would be to answer the question that they've asked you. And then if it's a formula, like maybe they've asked you for what is the molarity, then you're looking for molarity equals moles of solute over liters of solution. So if that's the case, then write down the formula and then go look in the question to see if you're given anything that you need to know there. So if you are, then you can substitute that in, and then that helps you to kind of focus on everything else is designed to help you find the part that you don't know yet. Sometimes you don't know either, and you have to kind of think, how will I find this? Like maybe how will I find the moles of solute? And then maybe how will I find the liters of solution? That's a simple example. So I do want to do a couple of problems with you that kind of show this to you. And always kind of go think through your process. I know your book talks about a roadmap. Think through the process as, how will I answer the question? What do I need to calculate that? Do your calculations, and then if there's a question to answer, make sure that you remember to answer the question. So in this example, which is from your textbook, we are talking about the density of air being 1.189 grams per liter, and it tells you that an object will float in air if its density is less than air. Of course, that means it would sink if its density is more than air. And then a chemist has created a thin-walled ball, kind of like a balloon that's a constant volume, a thin-walled ball that has a mass of only 0.12 grams. So the ball itself has a mass of 0.21 grams, and it's hollow, and the inside volume is 560 cubic centimeters. So the first thing that they want to know is, will the ball float if it's evacuated? So the first thing I need to think about is, how will I answer the question? So in order to do this, I need to decide by comparing the density to air's density, right? So this means that I need to calculate the density of just the ball, the empty ball, okay? And so only in part A, we're going to look at the density of just the ball, and then we'll compare. So density of the ball would equal the mass of the ball over the volume of the ball. And since it's thin-walled, its inside volume and its outside volume are the same. So we're going to see what we know. So we go back to the question, and we know both of these right away. We know that the mass of the ball is 0.12 grams, and we know that the volume of the ball is 560 cubic centimeters. However, I need to notice that if I'm going to compare this to air's density is in grams per liter. So I need to go ahead and change these cubic centimeters to liters. So I think of it this way, that 1 cubic centimeter is 1 milliliter. You should already have this in your equalities from what you've written down. And then 1,000 milliliters equals 1 liter. And so when I solve for the density of the ball in grams per milliliter, I discover that this is 0.21428. Let's talk significant figures here for a minute. Neither of my givens are exact. The 0.12 has 2 sig figs. The 560 has 2 sig figs because the 0 is not significant. Sig figs come in the next section. And then my 1-to-1 centimeters to milliliters is exact, which means it's an unlimited number of sig figs. And my 1,000 milliliters to 1 liter is exact as a definition, which means it's unlimited. So from my givens, then I have only 2 significant figures, which would be 0.21 grams per liter. Notice that centimeters cubed and milliliters have canceled. So I can compare the density of the ball to the density of the air, and the density of the ball is 0.21 grams per liter, and air is 1.189 grams per liter. So the density of the ball is definitely less. So now answer the question, the ball floats. Okay, so this is how you do this. So we're going to repeat this and see how this goes. And I'm going to actually do one more and then ask you to think about how you would do the other and come back and solve it for you. So that was part A. Let's change colors here so you can see a difference. Let's do part B. They want to know if it will float if it's filled with carbon dioxide. So now what I really need is the density of the ball plus CO2, which means that I need the mass of the ball plus the mass of the CO2 that would be in it over the volume of the ball and the carbon dioxide. But I need you to picture this is the volume together, which is going to be determined by the volume of the ball, which is really the volume of the ball. Okay, so that doesn't change. So let's look at what we know right now. We know the 0.12 grams for the mass of the ball, and we know the volume is 560 centimeters cubed. If you wanted to, at this point, you could have done this, 560 centimeters cubed to milliliters, milliliters to liters, and see that this would be, 1 liter and 1,000 milliliters. This would be 0.560 liters is the volume of the ball. So I'm going to go ahead and do that to save us some trouble. But I still need the mass of the carbon dioxide that would be inside. So let's talk about how we do this. I need to add a page. So to find the mass of the CO2, I need to use the density formula. And I'm going to actually use density as a conversion factor here to show you how this will work. So we know the volume of the CO2. And they gave us the density of the CO2 in the question. Okay, so I'm going to use dimensional analysis, and the density will be the conversion factor. This is a new conversion factor for you maybe. So I'm going to start with the 560 cubic centimeters. Remember that gases take the shape and volume of their containers. So the container has this volume, centimeters cubed. I'm going to go centimeters cubed. Actually, let's come back and change this. Since I already know that this is 0.560 liters, I'm going to just make this liters to grams of CO2. And this is all about the CO2 now, even though it's in that container. This was 1.830 grams. So notice that the density can be used as a conversion factor. And I find that this is now 1.0248 grams of CO2. Technically, I have two significant figures. This is not really 0.560, this is 0.56. So I have two significant figures, which means I'm really good to here. If I want to calculate with the whole thing, I can, or I can round it to 1.0, but I think when I did it, I waited to round, so I added in here 1.0248, and remember that that was my significant figure. Okay, so after I do that, this number comes up here. Now, after I do that, I can calculate the density of the ball. When I'm adding, remember that I'm looking at places after the decimal, so 0.12, and this is good to only the first place after the decimal, which means that I'll have only one place after the decimal, which is two total significant figures. We'll talk sig figs again later. And so this gives me the density of the ball as 2.0442, which I'm going to round to 2.0 grams per liter. The ball with carbon dioxide in it, right? So the density of the ball plus CO2 is 2.0 grams per liter, and the density of the air, is 1.189 grams per liter. And now the density of the ball is more than the density of the air, so the ball filled with carbon dioxide will not float, it will sink. Okay? So now here's what I want you to do. I would like you, oh, by the way, I want you to think about this. If the carbon dioxide by itself is more dense than the air, then putting it in the ball, it's going to even be more dense than that because it will have more the mass of the ball. So we could have technically answered this from here, that CO2 alone, the density is greater than the density of air, and so it sinks, right? But I wanted to show you how to do this so that you could practice it again. So now I'd like you to stop the video and do part C. Okay, and I will, I'll provide you with a little bit of work on this. I'm not going to take so long to talk through it, but I will provide you with a little bit of work for it, and then you can kind of go from there. So stop the video now and come back when you're done. Okay, welcome back. So in part C, we're going to do the exact same thing. The ball with hydrogen, the density of the ball plus the hydrogen is going to be the density, the mass of the ball plus the mass of the hydrogen over the volume together. Okay, so we know that this is 0.56 liters, and we know the mass of the ball is 0.12 grams, and so I need to do work now to find the mass of the hydrogen. So I'm going to do the same thing, 0.56 liters. They gave me the density as 0.0899 grams per liter, so 0.0899 grams of hydrogen per 1 liter, and that gives me, with two significant figures, of course, 0.050344 grams. And when I add that to the 0.12 grams, I'm good to the second decimal place. And so I can put that in, 0.050344 grams of hydrogen. And I can make sure that I'm good to the second decimal place in my answer. So the density together of the ball and the hydrogen will be 0.30418. I'm going to make that 0.30 grams per liter. Again, the density of the ball plus the hydrogen, and the density of the air, 1.189 and 0.30. This is less, so this will float. So you can kind of get an idea of how this works. And that, hopefully you were correct as you tried it on your own. And if not, then the second time through the explanation hopefully helped. All right, so let's shift gears a little bit. I want to do some dimensional analysis with you and just kind of show you a couple of other things here, remind you of metric conversions, things like that. And this has something that I call a conditional conversion factor. A chemistry professor, not me, I can maybe walk faster than this, can walk a mile in 15 minutes. That's a conditional conversion factor, and in this case, what this tells us is that 1 mile equals 15 minutes for this person, only for this person, all right? So now I can start my dimensional analysis. It wants to know how many minutes will it take to walk, this professor, to walk 10,500 meters. So I'm going to start here with my 10,500 meters. And actually, you don't need this conversion factor in that I gave you here. The inch is 2.54 centimeters, but this is a metric to English that you should memorize, so I always want to throw it your way. I'm going to go meters, and I'm looking to miles. So this is the other conversion factor I gave you. You would not have to memorize this, and so I'm going to go meters to miles, and this would be oh, can't do that because this is kilometers, sorry. I have to go meters. Sorry, I had a little bit of a step back there. Meters to kilometers, okay? And then kilometers to miles, and then miles to minutes, okay? So your metric conversions, this would be 1 kilometer is 1,000 meters. You need to memorize that. This is exact, so it has unlimited sig figs. You have 1 mile is 1.609 kilometers. This is not exact. So from that, the 1 mile is, but the 1.609 is not. So you have 4 sig figs there. And then 1 mile, 15 minutes. This is not exact either, which leaves us really with 2 significant figures from what we have here and 3 sig figs from here. And so when I do the math, 10,500 divided by 1,000 divided by 1.609 times 15, I get 97.8868 more numbers with 2 significant figures is 98 minutes. And you can check that meters cancel, kilometers cancel, miles cancel, and leave us with minutes. And then finally, let's do one more before we switch gears a little bit. In this case, let's read, within a cell, proteins are synthesized on ribosomes, assuming ribosomes are spherical. So this is the volume of a sphere formula given to you. What is the volume, there's my question, in decimeters cubed and in microliters of a ribosome whose diameter is 21.4 nanometers? So to find the volume, I'm going to use this formula, and that means that I need the radius. So I would actually probably also like to have that radius in decimeters so that I can find the volume in decimeters cubed. Okay, so I'm going to say that the radius equals 1/2 of the diameter, so that's 1/2 of 21.4 nanometers. And then I can either solve that right there, or I can just keep converting nanometers to meters and meters to decimeters. You should know both of these conversions. They are exact conversions. So this is 1 meter is 1 times 10 to the 9th nanometers, and 1 meter is 10 decimeters. And when I do this, I get 1.07 times 10 to the, it's a really small number, -7th decimeters is the radius. Okay, now I can substitute that in. Volume equals 4/3 pi times 1.07 times 10 to the -7th decimeters, and cubed, and that gives me, after I do the math, 5.13144 more numbers times 10 to the -21st decimeters cubed. I think in this I have 3 significant figures because all of my metric conversions are exact, and the 1/2 is really just a mathematical definition, not a measurement. So that leaves me with 5.13 decimeters cubed as, times 10 times 10 to the -21st decimeters cubed. And then if I want to convert that to microliters, I'm going to use the equality that gives me from cubic length to liquid volume. So I actually am going to do decimeters cubed to liters because those are 1-to-1 by definition, and that should be in your notes already. And then 1 liter is 10 to the 6th microliters, and that gives me 5.13 times 10 to the -15th microliters. And so there are my 2 answers. All right. If you need help with conversion factors, the unconventional conversion factors that you might see as you're doing work, and it's actually a really good video to watch anyway because it uses cube to cube, it uses cube to not cubed, It uses some things from chemical formulas, so it may be really helpful for you. There is a separate help video that looks like this, and so it might be helpful for you to watch that. All right, let's shift gears to the end of this, which is heat versus temperature. I do want you to know that heat is a type of energy, and it's actually the flow of energy by kinetic energy between two things. So from the thing that has a higher amount of energy to a lower amount of energy, so from the higher temperature to the lower temperature. Temperature is like a measurement of that kinetic energy. It's like a proportionality to kinetic energy. And so temperature is the measurement of the internal energy, and heat is the measurement of how it's transferred from one to another. So this is really good to read. You can come back and read all this, stop the video if you'd like, so that you can read all this and kind of get an idea, but this is kind of a complex concept, so it's important that you have a good understanding of that. Okay, and then finally, converting temperature units. We will not use Fahrenheit, but you should know that Celsius and Kelvin are the same scale, that 1 degree Celsius is the same as 1 Kelvin. It's just that Kelvin does not have negative values, so Kelvin is 0. Kelvin is absolute 0 when all kinetic motion stops. And that would be negative 273.15 Celsius. So we use that as our conversion. And when we do gas laws, we do a lot of converting to kelvins. And then something that you need to pay attention to is sig figs. Since sig figs are in the next section, you'll learn more again there. But remember that when you're adding and subtracting, you're worried about decimal columns. And so if your temperatures are given in whole numbers, then it's okay to use 273. But if you're given any decimals, you should use 273.15 to convert. All right, so hopefully this was helpful. You found something new, and I look forward to the next video.